What are gravitational waves?
So gravitational waves are ripples in the fabric of space and time. And according to Einstein's theory of general relativity, every moving object actually emits a tiny amount of gravitational waves, but the signal is too small for us to detect. So in order for us to detect gravitational waves, we need to wait for catastrophic events like the collision of two neutron stars.
What are neutron stars?
So neutron stars are some of the most exotic and dense objects in our universe. These stars weigh as much as our sun, but they're much smaller in size. A neutron star can extend up to 15, 70 miles across, and this is more or less the size of Washington, D.C.
Why is it such a big deal that we've discovered an electromagnetic counterpart to a gravitational wave signal?
Why is it such a big deal? So it's an entirely new level of knowledge. We've never ever been able to do this before. We've only just been able to detect gravitational waves for the last, 2 or so years, and we've only had 5 detected sources. This is the 5th detection. But this is the very first one that is accompanied by light. So that's accompanied by an electromagnetic counterpart. So now we have this opportunity to link together gravitational wave physics and astrophysics. So everything that's based on our knowledge, coming from observing photons. And that astrophysics represents stars and galaxies and growing supermassive black holes and neutron star mergers like this one.
Why is the detection of this source with Chandra important? What did it reveal about this cosmic collision?
So I think it was actually the very fast response of Chandra that was enabled us to actually look at the evolution of this source. And I think the evolution of this source is what makes it so important and interesting at X-ray wavelengths. So we were able to not detect something at 2 days, and then we were able to detect something 10 to 15 days later. So it's a very fast evolving source and really proved that the jet or the relativistic fire hose of emission was actually pointed away from us. So I think that was a really interesting thing that came from Chandra. Another thing that's really exciting about Chandra is it has very high angular resolution. And so why is that important for this source? Well, every galaxy in our universe will have some sort of X-ray emission, whether it be from stars in that galaxy called X-ray binaries, or from things called active galactic nuclei, which are at the very centers of galaxies. There's lots of sources of possible X-ray emission from any galaxy. Now, because this neutron star merger occurred very close in terms of, in the cosmic sense, in our own basically cosmic backyard, we're able to see all of this X-ray emission from that galaxy. So you can imagine if a neutron star merger occurred in that galaxy, it was also giving off X-ray emission. It's very difficult to actually find that neutron star merger amidst all this X-ray emission from the galaxy. Now, Chandra is very special because it has very high angular resolution to be able to pinpoint that neutron star merger and separate it from the position of the galaxy. So I think of it basically as using the best HDTV resolution that we have at X-ray wavelengths to be able to pinpoint that neutron star merger.
What questions remain? What will additional observations tell us?
Actually say that most of the questions still remain open, and maybe the most important of all is how this event compares to all the future ones we will detect. Is this an outlier, or is this representative of all neutron star mergers? And of course, the other question that is still open is how would a black hole neutron star merger look like across the spectrum?